And in this video we're going to run through a few examples of both finding inverse functions given an original function and proving that, say two functions are necessarily inverse functions, okay? And so let's start with from the last video, okay? In the last video we mentioned that inverse functions, or say given some f of x, we can find, since we're going to do it anyways, some f inverse of x. The definition of an inverse function, of course, basically says that given the original outputs of a function, some function, its inverse function would send them back onto the original inputs, okay? So you'll see this often, we'll write a function in terms of like roster notation. That's what this is called. It's called a roster notation. You know what a roster is. It's got people names on it. It kind of lists it out. But let's take a look at this original function f of x. Now, first thing we want to be able to do is find its inverse. So just using the definition of inverse, we could say, well, inverse functions take the original outputs and map them, when you plug them into the inverse, it maps them onto the original inputs of the original function. Then remember we say, then the domain and range basically have just switched around. So in other words, all of our original x's and y's switch around in the inverse function, okay? And the original outputs become the inputs of the inverse, and the original inputs become the outputs of the inverse. So we could say then the inverse function of this would be 1, 0. And instead of 1, 3, it'd be just 3, 1. Plug in 3, it gets mapped back onto 1. Plug in 5 here into the inverse, it'll map it back to the original 2. And of course, plug in 7. 7, it'll map it back onto the original 3. Now, part of this video is finding f inverse, and hey, congratulations, we just did. All we had to do was switch all the x's and y's around. We can define this as f inverse of x. However, I said we want to prove that these are inverses, okay? So one way to do it is to just, hey, eyeball this, look at it. All the x and y values have been switched around, but another way we could check this, is to see if all of these points would be reflected about the line y equals x, or what we call our identity function, okay? So now, what we'll do is we'll just plot a few. If my job is to prove that these are inverses, then say 0, 1 was on the original function. We better do those in blue. 0, 1 would be here. We say 1, 3, so up 1 over 3, over 2 up 5, over 2 up 5, over 3 up 7. Okay, I'm drawing really small here, Polly-Joes. Okay, so here's our original function. Now let's graph the other ones just to prove that these are inverses, but we see 1, 0, 3, 1, be 5, 2, and also 7, 3. So this is 5 here. So 7, 3. And we can see, ooh, not very good. Not very good there. We'll put 7 here. Make it look a little bit better. 7, 3. We can see that all of these points have been reflected about the line y equals x. So that would be one way to show that these are inverses. Analyze the graph. The other way is just to show that all the x's and y's have switched, okay? So now, a little bit more algebraically, if we head down here to g of x, we want to find g inverse of x, okay? So now remember, g of x is kind of like saying, hey, I'm the y values, the output values for your function, and then we have our x here. So to find the inverse of this algebraically, what we'll do is we'll take all the x's and y's and swap them. So instead of y equals 1/3 x plus 1, we'll have x equals 1/3 y plus 1, and then we need to solve for y. So now subtracting 1 from both sides, we get 1/3 y equals x minus 1, and then tripling everything here, we see that y equals 3x minus 3. Okay? So, or we could write this as, this is the inverse function of the original g, because we've switched the domain and range. We switched all the x's and y's around. We're saying, okay, so these two functions are inverses. We need to show that they are inverses. Okay? So one way to do this is, let's select a random input of the original function and output value. So let's say we plugged in, say, g of 0. Okay, g of 0 in this case, 1/3 times 0 is 0 plus 1 is 1. So we see the original 0 goes to 1, and of course that's our y-intercept of the first graph. We'll graph it in GeoGebra here in a second, but what if we took this original output of this function, we plugged it into g inverse, okay? So now we say, okay, so g inverse of 1. So g inverse of 1 would be 3 times 1 minus 3. Of course, we get 3 minus 3. We get an output value of 0. That is, when we plugged in the original output value 1 into its inverse, it mapped it back to the original 0, okay? Also, you know, and again, I said we'd look in a second here that they reflect about y equals x, but simply put, you know, 0, 1, and 1, 0 are definitely reflected about this y equals x line. And then, you know, the other way to check this was to plug one function into the other. That is, let us find, say, g inverse of g of x. That is, take all the original outputs, g of x values, and plug them into the inverse function, and we should map back onto just the original x values, or just x. So in this case, g inverse is 3 times our input minus 3, and since we're plugging in g of x, we know g of x is 1/3 x plus 1. So now distributing here, we get looks like x plus 3 minus 3. So in other words, we went back onto the original x value. Okay. And then we said the last way to check this is graphically, of course, but let's see. We had 3x minus 3. There he is. And then we also had 1/3 x plus 1. And so we can see that, you know, all of our points respectively have been reflected about this line, you know, y equals x. Okay. So now, those two cases being shown, we're going to observe a special case now. And this special case, oops, we don't want my calendar. The special case is the case of this parabola that I've got up here, h of x equals x squared. So let's go ahead and find our function inverse right off the bat. So we're going to start by switching our domain of range. In other words, switching all of our x's and y's around. So we get y equals x squared. We'll flip that around to x equals y squared. Okay. So x equals y squared. We need to solve for y now. So, you know, taking the radical of both sides, we get y equals plus or minus radical x. Now, this is interesting. This is interesting. And I say this is interesting because, and of course we could check this. You know, what if we plugged in, say, 1 into h? You know, h of 1 would be 1 squared is 1. So we have the point 1, 1 on the graph. Oh, well, let's not use that one. How about h of 2? h of 2 would be 2 squared is 4. That is, the point 2, 4 is on our original function. So 4, 2 must be on our output function. So what if we were to take the original output here, 4, and plug it into our h inverse of x, which is plus or minus radical x? What if we were to plug in 4 into this now? We say h inverse of 4, we should get plus or minus radical 4, which in this case is plus or minus 2. So the interesting thing is, when we plugged in the original output 4 into its inverse function, and I say that loosely here, we actually got 2 outputs. So what would this indicate? This would indicate that h inverse of x, when we put in one input, it actually spit out 2 outputs. And anybody who knows their algebra knows that when you put an input into a function, you are only supposed to get 1 output. Okay. So let's take a look at the original function here. We've got the original function. You know, as our parabola here, it looks like this, symmetrical through its, you know, vertical line through its vertex here. This is our original function. Now, what do we know about inverse functions? Well, we know all the points, they tend to switch the domain of range. That is, if the point 0, 0 is on here, then the point, you know, you flip around 0 and 0, you get 0, 0. So let's say we plug, or why don't we do our inverse function in red here. So 0, 0 would also be on its inverse. 1, 1 is on the original function, so switching 1 and 1, or the x and y around there, 1, 1 is also on the inverse function. But here comes the kick, okay? And it's this. The point, whoops, I don't want to color on that, but the point negative 1, 1 was on the original function. So on its inverse, and I'm not going to call it a function, then the point 1, negative 1 would be on there. 1, negative 1. So our inverse function, which is reflected about this line y equals x, actually looks like this. And so everything's kind of checking out here. It looks reflected. It's just this. If I were to ask an algebra student, would you say that h inverse right now, it is a relation, but would you also call it a function? And the answer to that is simply no, because it doesn't pass the vertical line test. That is, for a given x value, there are more than one output value. So let's think about this. In general, you know, how could we have looked at the original function and known before we had started that its inverse was would be a function or not, you know, 1 to 1? And I think the answer to that is yes. If we know that it is going to reflect about the line y equals x. Okay, then we know this. If its inverse doesn't pass the vertical line test, what if we inverted this vertical line about the line y equals x? What if we reflected it about there? It would have been a horizontal line. Okay, so here's another kicker here, but basically we could use what we call the horizontal line test. If we are able to draw a horizontal line through the original function x squared, and it would strike it 2 or more times. That means that when we find its inverse, and it is reflected about the line y equals x, then its inverse will not pass the vertical line test. Okay, so we'll do more with the horizontal line test in one more video, but basically, looking at the original, if a horizontal line passes through it 2 or more times, then when we find its inverse, you're going to have a vertical line that passes through it 2 or more times. In other words, its inverse is not itself a function, it is just a relation. Okay, so cool.